Welcome to the channel. Today we'll be doing some more statistics. Last video we were working on Unit 8 for 2 hours. We did random variables and probability distributions, and that involved discussing things like the normal distribution, how to perform operations with two sets of expected values or means and standard deviations. We dealt with theoretical probabilities as well. And we also discussed things like binomial random variables and different kinds of distributions. And we also talked about things like assumptions for independence and how sample sizes can mimic true independence. Today we'll also be going through Unit 9, which has to do with sampling distributions, and just quickly reading through what I've wrote the other day. This unit will essentially talk about why we can make certain assumptions using distributions and why statistics works, I guess. That sounds kind of vague, but that's kind of what it is, though. I guess that's every unit, but okay. Let's just get straight into the math. We will start off with identifying binomial variables and see how we go from there. There were 3 conditions for random variables being classified as a binomial, so outcomes are classified as either a success or a failure, independent trials, fixed number of trials, and that's about it. There's a 4th one, but it's kind of redundant to one of the other points, so I don't remember that one. Okay. Without replacement. Nope. So independent. There's no fixed number of trials. Okay, let's move on to the next. We've watched a couple of videos here, but I guess it won't hurt to watch them again. At least quickly go through them.
Let's say that you know the probability of making a free throw. You know that the probability of missing a free throw is percent. What we're curious about is the probability of exactly two scores in. If you get inspired at any.
Yeah, okay. I remember how to solve this, so this is a combinatorics problem. We find the probability of getting 2 scores in 6 attempts, and because trials are independent, the way of getting 2 scores initially or 2 scores in the last 6, or any combination of 2 scores within 6, would be equivalent. So we get the probability of exactly 2 scores in 6 attempts, just one version of that, and then we multiply that by the number of ways to to have 2 scores within 6 attempts.
The point in this is and hopefully you don't get the
So this is one case.
multiplication symbols confused to get 2 scores to a second different 3 number way from efficient notation.
Yeah, and then it's combinations. So number of trials factorial over the number of successes, I think. Something like that.
This factorial to be equal to
Yeah. Then 6 minus. Yep.
cancel.
Okay.
Right would be 81.
Pretty straightforward.
But I'm multiplying 4. Setting us up this way, 80% free throw.
And this video shows how to generalize this. Exactly K and N.
Score. Think about the probability distribution for a random variable that's defined by the number of scores in your n attempts, or the number of scores in your 6 attempts.
Yep.
So in the last video, we studied a circumstance where I had a
binomial probability distribution.
What is the percentage that time proc 0 times or what that over 0.1 so left is 0.70.
This table just shows what the probabilities are of getting exactly 0, exactly 1, exactly 2, etc. successes in the free throw example.
Percent. These things
So
for the
that's
random
pretty
variable in question.
straightforward as well.
Visualizing it, but it's in the last video, we worked through essentially the probability distribution for this random variable defined as the number of free throws you make when taking 6 free throws, assuming you have a 70% free throw percentage. And I suggested that, hey, why don't you visualize this, draw the graph this probability distribution, this binomial probability distribution. And when I thought about it, I said, well, I too would enjoy graphing it, and we might as well do it together because whenever you graph these things, it makes it very visual and kind of the shape of a binomial distribution like this. So let's do that. So let me maybe move over to the right a little bit.
It's probably going to make some left skewed thing.
Right there. It was like, hey, how does this change
this
right. binomial distribution? And you can do that on a spreadsheet and actually see how
it makes sense because I don't think it shows here, but 0.7 was the free throw success rate, and so it makes sense that if you do 6 shots over and over and over again, that you'd be above the middle point because you succeed more than you fail.
Change.
Binom PDF. I think this is a calculator thing. I don't actually have a calculator emulator on my computer.
Do in this video is use a statistics test. What is the probability of making 4 out of 7 free throws? Well, this is a classic binomial random variable question. If we said the binomial random variable x is equal to number of made free throws from...
What is the probability of making 4 out of 7 free throws? Okay. 7C4. Seven, choose 4. Calculate 35. So this reads as 45 ways, 35 ways to organize 4 within 7 objects. It'd be 35 times 4 14.42%.
Probability for those and you 7 and once
X is 0.14. What is the probability of making less than 5 free throws? So it's 1, 2, 3, 4. Or he showed it like this.
and the probability of success in each trial is 0.35. And now 3 or 4 free throws. And once again, 7 trial binomial random variable. So once again, I can go to second distribution. I'll scroll up to go to the bottom of the list. And here you see it, binomial cumulative distribution function. So let me go there, click enter. And once again, 7 trials. My p is 0.35. And my x value is 4. But now this is going to give me the probability that my binomial random variable equals 4. This is going to give me the probability that I get any value up to and including 4. So this should be a higher probability. And there you have it. It is
continuous, wait, cumulative. Probability distribution versus cumulative. Okay.
approximately 0.94. So this is approximately 0.94. So hopefully you found that helpful. These calculators can be very useful, especially on something like an AP Stats exam.
Nice. Okay. Binomial probability basic. Oh, this is just... Oh, Google Classroom. Interesting. Never noticed that. Two of the 3 free throws. 1 miss. They're all the same because these are binomial variables. Use the combination formula to verify that these 3 ways represent every way we can arrange 2 makes in 3 attempts. So 3 factorial over 1 factorial times 2 factorial. 2 times 1 times 1 is 2. 3 times 2 is 3, right? Now put it all together to find the probability that she makes exactly 2 of the 3 free throws. Pretty sure it's just this times 3. So 0.243. Then this is asking us to recreate what Sal was trying to teach us in that other video. You can build a formula for this type of problem, which is called a binomial setting. Well, these are the 2 conditions for a binomial variable that I feel are pretty much the same thing, but maybe there are ways to violate one but not the other. I guess they are different. Because 2 things could have the same probability of success, but actually be dependent on one another, maybe somehow. And this is just a long way of saying you get the probability for one scenario, and then you multiply it to all the ways to get that scenario using the combinations formula. In general, yeah, so this first half, the combinations part, the capital C, that's all the ways that you can succeed given what you're looking for. So all the possible success, all the possible combinations for success. And then you multiply it to the number of successes you have within the trials multiplied by the number of failures you have, and with respect to their probabilities as well. 20% chance. I'm going to shoot 4 free throws. So it'd be 0.2 times 0.2, 0.8 times 0.8. Where did it go? Oh, yep, okay. Then we would do 2 factorial 4, or 4 factorial. Six. What is the probability that he makes 3 or more of the free throws? So it's 3 or 4. Probability 3 or 4. Um, that's for 4 because there's only one way to do 4. You can't really organize it. There's only one combination for 4, is what I'm trying to say. And then for 3, it would be the exact same as this. Four times, kind of lost it. I don't know why I'm doing this manually. I'm kind of stupid. I don't think that's right. It's too small. Maybe. Yeah. Four, three, calculate. Four. feels like yep. Sometimes I just like trying to do it mentally, just to wrap my head around certain formulas so that I really understand each part, but don't have to do that. Okay. One albino plant among 6 offspring. Okay. It's one of these two. It's this one. Exactly 3 heads. It's one of these. Wait, okay. Because this says at least 2, we can actually just solve for the one case that it's not 2 or 3, so just 1. So it's the same values, so 1 minus this should give us that. Makes at least 2 of 3. Let's see. Yep, exactly 2 prizes, so we're solving for one condition. So this is the probability that he gets exactly one answer right in a set of 6 questions. So 1 right, 5 wrong. And then we multiply it to the combinations. So 6C, 5, 1. Yeah, so it's 6. Just double checking. Okay, and then we do the same thing, but this will be 2, and this will be 3, and this will change as well. And this will be 4. 6 questions. Right. Then we do 6C to calculate. There's 15 ways to do that. Oh, right, there's one more. Fewer than 2. Ah, well, I got it wrong anyways. Other hand, because I did 1 and 2 instead of 0 and 1. Okay, let's just finish this off. Ah, we can take a break. Exactly, 2. Okay. This one's pretty easy. Okay, so 0 point. Curious to see if this is exactly the same. Yeah, it's exactly the same. 0 0.2. Oh man. Oh, what am I doing? It's 0 0.1. Restart. Ah, do we have to restart? Now I'll remember later. It's fine. Next.
So I've got a binomial variable x, and I'm going to describe it in very general terms. It is the number of successes after n trials, where the probability of success for each trial is p. And this is a reasonable way to describe really any binomial variable. We're assuming that each of these trials are independent. The probability stays constant. We have a finite number of trials right over here. Each trial results in either a very clear success or failure. So what we're going to focus on in this video is, well, what would be the expected value of this binomial variable? What would the expected value of x be equal to? And I will just cut to the chase and tell you the answer. And then later in this video, we'll prove it to ourselves a little bit more mathematically. The expected value of x, it turns out, is just going to be equal to the number of trials times the probability of success for each of those trials. And so if you wanted to make that a little bit more concrete, imagine if a trial is a free throw each of those trials. It turns out is just going to be equal to the number of trials times the probability of success for each of those trials.
Yeah, that
And so if you
makes
wanted to make that a
sense.
little bit more concrete, imagine if a trial is
Yeah, like coin flip with a weighted coin, 0.6 for heads, 0.4 or 0.6 for heads. And then you have 3 trials, 3 coin flips. It'd just be 0.6, 0.6, 0.6 if you're looking for the probability that you get 3 heads right.
a free throw, taking a all within the state's 10. So this is making it all a lot more concrete. The number of trials times the probability of success in any one of them. Well, if you're taking 10 shots with a 30% free throw percentage, it actually does feel natural that I would expect to make 3 shots. Now, with that out of the way, let's make ourselves feel good about this mathematically, and we're going to leverage some of our expected value properties. In particular, we're going to leverage the fact that if I have the expected value of the sum of 2 independent random variables, let's say x plus y, it's going to be equal to the expected value of x plus the expected value of y that we talk about in other videos. And so, assuming this right over here, let's construct a new random variable. Let's call our random variable y. And we know the following things about y. The probability that y is equal to 1 is equal to p, and the probability that y is equal to 0 is equal to 1 minus p. And these are the only 2 outcomes for this random variable. And so you might be seeing where this is going. You could view this random variable, it's really representing one trial. It becomes 1 in a success, 0 when you don't have a success. And so you could view our original random variable x right over here as being equal to y plus y, and we're going to have 10 of these. So we're going to have 10 y's. In the concrete sense, you could view the random variable y as equaling 1 if you make a free throw and equaling 0 if you don't make a free throw. It's really just representing one of those trials, and you can view x as the sum of n of those trials. But actually, let me be very clear here. I immediately went to the concrete, but I really should be saying n y's because I want to stay general right over here. So there are n y's right over here. This was just a particular example, but I am going to try to state general for the rest of the video because now we are really trying to prove this result right over here. So let's just take the expected value of both sides. So what is it going to be? So we get the expected value of x is equal to, well, it's the expected value of all of this thing, but by that property right over here, this is going to be the expected value of y plus the expected value of y plus, and we're going to do this n times, plus the expected value of y, and we're going to have n of these. So we have n. And so you could rewrite this as being equal to, so this is our n right over here. This is n times the expected value of y. Now, what is the expected value of y? Well, this is pretty straightforward. We can actually just do it directly. The expected value of y, let me just write over here. The expected value of y is just the probability weighted outcomes. And since there's only 2 discrete outcomes here, it's pretty easy to calculate. We have a probability of p of getting a 1, so it's p times 1, plus we have a probability of 1 minus p of getting a 0. Well, what does this simplify to? Well, 0 times anything, that's 0, and then you have 1 times p. This is just equal to p. So expected value of y is just equal to p, and so there you have it. We get the expected value of x is 10 times the expected value, or the expected value of x is n times the expected value of y, and the expected value of y is p, so the expected value of x is equal to n. What we're going to do in this video is continue our journey trying to understand what the expected value and what the variance of a binomial variable is going to be, or what the expected value or the variance of a binomial distribution is going to be, which is just the distribution of a binomial variable. And so, like in the last video, I have this binomial variable x that's defined in a very general sense. It's the number of successes from n trials, so it's a finite number of trials, where the probability of success is equal to p, so the probability is constant across the trials for each of these independent trials. So the probability of success in one trial is not dependent on what happened in the other trials. And we also talked in that previous video where we talked about the expected value of this binomial variable, is we said, hey, it could be viewed, this binomial variable can be viewed as the sum of n of what you could really consider to be a Bernoulli variable here. So this variable, this random variable y, the probability that's equal to 1, you could view that as a success, is equal to p. The probability that it's a failure, that y is equal to 0, is 1 minus p. So you could view y, the outcome of y, is really...
He used the new term Bernoulli variable. And I'm trying to think. We've talked about Bernoulli experiments before, but not Bernoulli variables. I guess it's just a variable within the... it's really hard to talk this morning.
Or whether y is 1 or 0 is really whether we had a success or not in each of these trials. So if you add up n y's, then you are going to get x. And we use that information to figure out what the expected value of x is going to be. Because the expected value of y is pretty straightforward to directly compute. Expected value of y is just probability weighted outcomes. So it's p times 1 plus 1 minus p times 0 times 0. This whole term is going to be 0. And so the expected value of y is really just p. And so if you said the expected value of x, well, that's just going to be, let me just write over here, this is all review. We could say that the expected value of x is just going to be equal to, we know from our expected value properties, that's going to be equal to the sum of the expected values of these n y's. Or you could say it is n times the expected value of y. The expected value of y is p, so this is going to be equal to n times p. Now we're going to do the same idea to figure out what the variance of x is going to be equal to. Because we know from our variance properties, you can't do this similarly, and the variances of these n y's. So it's going to be similarly n times the variance, n times the variance of y. So this
Variance. You need the mean to calculate the variance. You get the difference between the actual values and the mean. You square that, you add them up, and then you square root their sum.
all boils down to what is the variance of y going to be equal to. So let me scroll over a little bit, get a little bit more real estate, and I will figure that out right over.
In this case, because they're all going to be the same, you would just do, let's see
right
actually,
over here.
what does
All
he
right,
use?
so we want to figure out the variance, the squared distances from the expected value. So
Squared
we have a
distances,
probability
yeah.
of, you're going to get a 1 with a probability of p. So in that case, our distance from the mean, or from the expected value, we're at 1. The expected value we already know is equal to p.
Yep.
So that's that for that possible outcome, the squared distance times its probability weight. And then we have, actually let me scroll over a little, well, I'll just do it right over here. Plus, we have a probability of 1 minus p for the other possible outcome. So in that outcome, we are at 0. And the difference between 0 and our expected value, well, that's just going to be 0 minus p. And once again, we are going to square that distance.
Why does he make it 0?
And so this is the expression, or square that quantity. And so this is the expression for the variance of y, and we can simplify a little bit. So this is all going to be equal to, so let me just, p times 1 minus p squared. And then this is just going to be p squared times 1 minus p plus p squared times 1 minus p. And let's see, we can factor out a p times 1 minus p. So what is that going to be left with? So if we factor out a p times 1 minus p here, we're just going to be left with a 1 minus p. And if we factor out a p times 1 minus p here, we're just going to have a plus p. These two cancel out. This whole thing is just a 1. So you're left with p times 1 minus p, which is indeed the variance for a binomial variable. We actually proved that in other videos. I guess it doesn't hurt to see it again. But there you have it. We know what the variance of y is. It is p times 1 minus p. And the variance of x is just n times the variance of y. So there we go. We deserve a little bit of a drum roll. The variance of x is equal to n times.
Stuff like this, I feel that you should understand. I don't like it when people just simplify it and without the proof. I'm not even sure if you would call this a proof, but it's good to know, I guess.
P times 1 minus p. So if we were to take the concrete example of the last video, where if I were to take 10 free throws, so each trial is a shot, is a free throw. So if I were to take 10 free throws, and my probability of success is 0.3, I have a 30%
P is a given.
free throw percentage. The variance that I would expect to see, so in that case, the variance
Would be 0.3 times 0.7.
if x is the number of, and so that would be 0.2 equal to 2.1. And if I wanted to figure out
The variance of 10 free throw shots.
standard deviation of this right here, I would just take the square root of this.
Yeah, okay. Makes sense. I understand the broken down formula, but I don't understand how we got there. I'm sure it would make sense if I had spent more time on it, but...
We're told a company produces processing chips for cell phones, and one of its large...
Okay, we need to calculate mean and standard deviation. 500 chips. 2% defective. Okay. Let's try and recall pondering. Pretty sure the mean is just NP, right? So 500 times 0.02, that's 10. So that's the mean. That's the expected value of 500 chips, given the success value for success, or probability for success in each trial. And then the variance would be 1 times 1 minus p, or p times 1 minus p, which is 0.02 times 0.98. And then you would just get the square root of that to get the standard deviation. So let's see.
The fact they only have style time probability, and so times minus the 500, 1 minus the 0 sign long enough to be equal to.
Oh,
well, let's see, 500.
And I forgot the part where you multiply it.
Times 0, and I get
That's fine.
deviation. If I wanted the variance, it would be 9. This is approximately
Nice, okay.
3.1.
Oh, it's easy enough. That is the mean. And then the standard deviation would be 50 times 1 times 0.75. Is that right? No. Let's see where we went wrong. Fail hard, fail fast. Eh? Did I forget the square root? Yeah, I did. Okay. Okay. 25, 100 times 0.25 times come on, dude. Ten. Bonus question. Oh, in a purchase. Okay. So it's actually just 15. So they would get 4.5. And here they would get something like this. Okay. Quiz. Mean standard deviation of eggs. At most, one prize. That's the same as just one prize, I think. So, go. Let's do the full formula. 1 in 4 boxes, 5 boxes. Probability that she gets at most one prize. So, let's do the first part. One prize, 4 non-prizes. And then combinations. One way to arrange in 5. There's 5. Exact decimal. Say 0.4. What did I do wrong? I keep forgetting the 0. Ah. Okay, redo. Oh, standard deviation. Almost got that wrong. It doesn't mention if it doesn't mention independence, so I'll assume it's not. Hey, it didn't improve this. What the heck? Okay, let's just do it. Nope, wrong. It's supposed to be 4 and 5. Mm-mm. Nope. Ah, damn it. Yeah, take a break. It's like an hour in and almost an hour in. It's an hour in including the breaks, but I'm feeling pretty good. These breaks, I feel I should be doing more. Just helps me reset and come back to the questions and yeah, Pomodoro. Great strategy, I guess. Okay, what did I do wrong? What did I do wrong? Ugh, last four questions. Stupid. Okay, same thing. We go like that. Five possible choices. No, like this. Okay, probability of 0.75 times 5. Okay. Think that's right. Let's see. Okay, 0.25, one prize, four fails, five ways to rearrange, one within five, sample of one, relation trials of five. Okay. 0.63. Easy. Boom. Okay. Next. No, go here.
So I have two different random variables here, and what I want to do is think about what type of random variables they are. So this first random variable, x, it's equal to the number of sixes after 12 rolls of a fair die. Well, this looks pretty much like a binomial random variable. In fact, I'm pretty confident it is a binomial random variable. We could just go. So I have two different random variables here, and what I want to do is think about what type of random variables they are. So this first random variable, x, it's equal to the number of sixes after 12 rolls of a fair die. Well, this looks pretty much like a binomial random variable. In fact, I'm pretty confident it is a binomial random variable. We could just go down the checklist. The outcome of each trial can be a success or failure. So trial, outcome, success, or failure. It's either going to go either way. The result of each trial is independent from the other ones. Whether I get a 6 on the third trial is independent on whether I got a 6 on the first or the second trial. So result, let me write this trial. I'll just do a shorthand trial. Results, independent. Independent, that's an important condition. Let's see, there are a fixed number of trials. Fixed number of trials. In this case, we're going to have 12 trials. And then the last one is we have the same probability on each trial. Same probability of success. Probability on each trial. So yes, indeed, this met all of the conditions for being a binomial random variable. And this was all just a little bit of review about things that we have talked about in other videos. But what about this thing in the salmon color, the random variable y? So this says the number of rolls until we get a 6 on a fair die. So this one strikes us as a little bit different, but let's see where it is actually different. So does it mean
Trial results. It's pretty much the same on everything except fixed number of trials.
that the trial outcomes, that there's a clear success or failure for each trial? The outconstraint, first have the independence. This third condition for a reason, because we clearly don't have a fixed number of trials. Over here, we could roll 50 times until we get a 6. The probability that we'd have to roll 50 times is very low, but we might have to roll 500 times in order to get a 6. In fact, think about what the minimum value of y is and what the maximum value of y is. So the minimum
0
value that this random variable can take, I'll just call it min
1.
y, is equal to what?
Whoops.
Well, it's going to take at least one roll, so that's the minimum value. But what is the maximum value for y? And I'll let you think about that. Well, I've assumed you've thought about it if you pause the video. Well, there is no max value. You can't say, oh, it's a billion, because there's some probability that it might take 1,000,000,001 rolls. It is a very, 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 very small probability, but there's a type of random variable where it meets rolls, a Googleplex rolls. So you can imagine where this is going. So this type of random variable, where it meets a lot of the constraints of a binomial random variable. Each trial has a clear success or failure outcome. The probability of success on each trial is constant. The trial results are independent of each other, but we don't have a fixed number of trials. In fact, it's a situation where we're saying, how many trials do we need to have until we get success? Maybe that's a general way of framing this type of random variable. How many trials until success? While the binomial random variable was how many trials, or how many successes, I should say, how many successes in finite number of trials. So if you see this general form and it meets these conditions, you can feel good it's a binomial random variable. But if we're meeting this condition, clear success or failure outcome, independent trials, constant probability, but we're not talking about successes in a finite number of trials, we're talking about how many trials until success, then this type of random variable is called a geometric random variable. And we will see why in future videos it is called geometric, because the math that involves the probabilities of various outcomes looks a lot like geometric growth or geometric sequences and series that we look at in other types of mathematics. And in case I forgot to mention, the reason why we call binomial random variables is because when you think about the probabilities of different outcomes, you have these things called binomial coefficients based on combinatorics. And those come out of things like Pascal's triangle, and when you take a binomial to ever-increasing powers. So that's where those words come from. But in the next few videos, when you think about the probabilities of different outcomes, you have these things called binomial coefficients based on combinatorics. And those come out of things like Pascal's triangle, and when you take a binomial to ever-increasing.
And this could be neither because it doesn't say independence, but I knew it. Damn it. Damn. Okay. Number of questions before she misses one. Oh, missed that part. Okay, let's try again. No way, it's binomial. But it doesn't say anything about independence. Okay, it's kind of stupid, but okay. This is geometric, no way. It has to be neither because there's a fixed number of trials. There's a fixed number of trials, independent. Different student each week. So that means it's not constant probability, so it has to be neither. Okay. Okay.
So let's say we're going to play a game where on each person's turn, they're going to keep rolling this fair six-sided die until we get a 1.
Volume's a bit low
and
on
we just
this
want to see
one.
how many rolls does it take. So let's say we define some random variable, let's call it x, and let's call it the number of rolls until we get a 1. So what's the probability that x is equal to 1? Pause this video and think about it. All right, the probability that x is equal to 1 means that it only takes us one roll to get a 1. Well, that's going to be a 1/6 probability. Well, what's the probability that x is equal to 2? Well, that means that on the first roll, we get something other than a 1. So that is going to be 5/6. And then on the second roll, we get a 1. So that has a 1/6 probability. And we could keep going. What's the probability that x is equal to 3? Pause the video and think about that.
Yeah, 5, 6, 5, 6, 1, 6.
Well, that means we miss on the first two, so we have a 5/6 chance of getting something. The third type of random variable or independent, we're dealing with a geometric random variable. Now, one question is what is going to be the mean of this geometric random variable? Well, we proved in another video where we talk about the expected value of a geometric random variable. We're really talking about the mean of a geometric random variable. And it is a little bit intuitive. If you were to just guess what is the mean of a geometric random variable where the chance of success on each roll is 1/6, you might say, well, maybe on average it takes you about 6 tries, and you would be correct. The mean of a geometric random variable is 1 over the probability of success on each trial. So in this situation, the mean is going to be 1 over, the probability of success in each trial is 1 over 6, so it's equal to 6. So one way to think about it is, on average, you would have 6 trials until you get a 1. Now, another question is, what's a measure of the spread of a geometric random variable? And we don't prove this in another video, maybe I'll do it eventually, that the standard deviation of a geometric random variable is the mean times another random variable. Well, we proved in another video where we talk about the expected value of a geometric random variable. We're really talking about the mean of a geometric random variable. And it is a little bit intuitive. If you were to just guess what is the mean of a geometric random variable where the chance of success on each roll is 1/6, you might say, well, maybe on average it takes you about 6 tries, and you would be correct. The mean of a geometric random variable is 1 over the probability of success on each trial. So in this situation, the mean is going to be 1 over, the probability of success in each trial is 1 over 6, so it's equal to 6. So one way to think about it is, on average, you would have 6 trials until you get a 1. Now another question is, what's a measure of the spread of a geometric random variable? And we don't prove this in another video, maybe I'll do it eventually, that the standard deviation of a geometric random variable is the mean times the square root of 1 minus p, or you could just write this as the square root of 1 minus p over p. Now in this situation, what would this be? Well, the standard deviation of this random variable, this geometric random variable, it's going to be the square root of 1 minus 1/6, all of that over 1/6. So this is going to be equal to the square root of 5/6 over 1/6, which is equal to 6 times the square root of 5/6. And this is going to be approximately equal to 5 divided by 6 is equal to that. We'll take the square root of that and then multiply that times 6. It gets us to about 5.5. So approximately equal to 5.5. And what's interesting about a geometric random variable, obviously the lowest value here in this case is 1, 2, 3, can go higher and higher, but it can go arbitrary. You could get really unlucky, and it might take you 1,000 rolls in order to get that 1. It could take you a million rolls, very low probability, but it could take you a million rolls in order to get that 1. And so another thing to realize about a geometric random variable's distribution, it tends to look something like this, where the mean might be over here. And so you have a very long tail to the right of your mean. And this is classic right skew. And so all geometric random variables distributions are right skewed. They have a long tail of values, an infinitely long tail of values they can take to the right. Now, one last question. Instead of dealing with a 6-sided die, what would be the situation if we were dealing with a 12-sided die? What would then be the mean of our random variable?
It'd be 12.
And what would be the standard deviation of our random variable?
Standard deviation would be 1 minus 1 over 12, or the square root of that, over 1 over 12, right?
We'll pause this video. We're playing that first. We write this in 12s. 11 divided by 12, 11 variable. And then you have a standard deviation that goes a reasonable bit on either side of the mean. It's almost equal to the mean, actually in both situations. It's a little bit lower than the mean. But then there's many, many, many values that go far to the right of your mean. And so you have this classical right skew for a geometric random variable.
That sounds good. Okay, find the mean and standard deviation. Okay. 1 over 1 divided by, or 0.21, right? That's the mean. One minus that. P squared at the bottom. Divided by P squared, 1 minus P. Like that. Hmm. Where'd the rest of my equation go? This is 100% gonna be wrong. No. Oh, what am I doing? Wait, what? No, let's try again. check again. Oh wait. Content. Oh no. Why am I doing 0.58? Oh my god. One minus p, square root of that, divided by p, rounded up. What am I doing? Give me a second. Okay. Standard deviation. 1 minus 0.97. Square root of 0.03. And then we do this divided by 0.2 items. Oh my god, where did I go wrong? Ah. Yeah. Okay. 0. Miss his first free throw. Okay. So 1 out of 5. 1 divided by 0.2, that's 5. Oh, that's so lame. Oh. Oh my God, that's because I used 0.8 zeros. No. Again. Mm, 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 mm. Oh, why did I do 3 out of 5? It's so confusing. Not really, I'm just being lazy, but okay, I guess we'll try again. It's a bit morbid to say dead. Children are in this platform. Okay, for every 4 quotes in the database, 3 of them are from dead people. 3 out of 4. 1.3. No. Standard deviation would be... No, got it wrong. Eh, no, got it right. Okay, break. Oh, damn. I didn't even realize I forgot to stop recording. Whoops. Okay, well, we're back now. And, yep. Okay. Start. Mean. What are we looking for? To reach first page with a diagram. 2 of 3 pages have diagrams, so that one's pretty easy. Just do 1/3 because that's 2/3 minus 1, and then we do this what the this question is so confusing. Maud reaches the traffic light before she has to stop at it. Before she has to stop? Yeah, whatever, that doesn't make sense, but could have just said green or red and Jesus. Yeah. 2.3. Stupid. Wait. I'm stupid. Ah, god damn it. No. Come on again. Double rainbows. Okay. Straightforward. We're doing the inverse of that, so P is 0.58. Okay. Nope. Easy. Okay.
Jeremiah makes 25% of the 3-point shots he attempts, far better than my percentage. For warm-up, Jeremiah likes to shoot 3-point shots until he successfully makes one. All right, this is a telltale signs of a geometric random variables. How many trials do I have to take until I get a success? Let M be the number of shots it takes Jeremiah to successfully make his first 3-point shot. Okay, so they're defining the random variable here, the number of shots it takes, the number of trials it takes until we get a successful 3-point shot.
Find the probability that Jeremiah's first successful shot occurs on his third attempt. That would just mean that you fail, fail, and then you succeed, right?
Assume that the results of each shot
So 0.75, 0.75,
are
0.25.
the numbers that's what we're aiming for. Or another way to think about it,
Okay, that was pretty easy. D equals 4. D be the number of stray dogs until she finds one with a microchip. Okay, so like this. Um, on the sixth order of the day. Okay, so this would be 10 to the power of 5.
Amelia registers vehicles for the Department of Transportation. Sports utility vehicles, also known as SUVs, make up 12% of the vehicles she registers. Let V be the number of vehicles Amelia registers in a day until she first registers an SUV. Amelia registers vehicles for the Department of Transportation. Sports utility vehicles, also known as SUVs, make up 12% of the vehicles she registers. Let V be the number of vehicles Amelia registers in a day until she first registers an SUV. Assume that the type of each vehicle is independent. Find the probability that Amelia registers more than four vehicles before she registers an SUV. So let's just first think about what this random variable V is. So it's the number of vehicles Amelia registers in a day until she registers an SUV. So for example, if the first person who walks in the line or through the door has an SUV and they're trying to register it, then V would be equal to 1. If the first person isn't an SUV, but the second person is, then V would be equal to 2, so forth and so on. So this right over here is a classic geometric random variable right over here. It's a geometric random variable. We have a very clear success metric for each trial. Do we have an SUV or not? Each trial is independent. They tell us that. They're independent. The probability of success in each trial is constant. We have a 12% success for each new person who comes through the line. Now, the reason why this is not a binomial random variable is that we do not have a finite number of trials. Here, we're going to keep performing trials. We're going to keep serving people in the line until we get an SUV. And so what we have over here, when they say find the probability that Amelia registers more than 4 vehicles before she registers an SUV, this is the probability that V is greater than 4. So I encourage you, like always, pause this video and see if you can work through it. And we're going to assume that she's just not going to leave her, I guess, her desk or wherever the things are being registered. She's not going to leave the counter until someone shows up registering an SUV. So we will just keep looking at people, I guess we could say over multiple days, forever. She'll work for an infinite number of years just for the sake of this problem until an SUV actually shows up. So try to figure this out. All right, now I'm assuming you...
I would do V equals 1, 2, 3, and then minus that by 1 because probability adds up to 1.
You've had to go. And some of you might say, well, isn't this going to be equal to the probability that V is equal to 5 plus the probability that V is equal to this? This is, summing up, it is less than or equal to 4. Well, that's the same thing for the customers. Or what's the probability that for each customer she goes to that they're not an SUV? Well, that's 1 minus 12% or 88% or 0. Calculate. And so let's get our calculator out. And so I'm going to get I'm going to get 0.88 and I'm going to raise it to
First cars are not SUVs.
the 4th power, and I get, and I'm just going to round it to the nearest, let's see, do they tell me to round it? Okay, I'll just round it to the nearest, I guess, well, 100th, well, I'll just write it as 0.5997 is equal to 59, that she is going to have to see more than 4 customers.
Cumulative probability, eh? Less than a value. Then it'd just be...
Liliana runs a cake
Is
decorating.
the other one greater than a value? It's literally the same thing, but...
Cake decorating business, for which 10% of her orders come over the telephone.
Find probability that it takes fewer than 5 orders for Liliana to get her first telephone order of the month. Over here, then we wouldn't do the 1 minus. Fewer than 5, so that's just 1, 2, 3, and 4.
Let C be the number of cake each 10%. There's a 92 orders actually get the is. So what's this? Well, because this is just saying what's the probability we do have an order in the first.
Let's actually watch
through
it, not be lazy.
Geometric random variable. Now they ask us find the probability that it takes fewer than 5 orders for Liliana to get her first telephone order of the month. So it's really the probability that C is less than 5. So, like always, pause this video and have a go at it. And even if you struggle with it, that's better. Your brain will be more primed for the actual solution that we can go through
Yeah,
together.
that is pretty good.
So I'm assuming you've had a go at it. So there's a couple of ways to approach it. You could say, well, look, this is just going to be the probability that C is equal to 1, plus the probability that C is equal to 2, plus the probability that C is equal to 3.
This
plus
stuff makes sense to me, but I wonder how,
and
like,
we can calculate it this way. What
how
is the probability that
regular
C equals
people
1?
feel.
Well, it's the
How
probability that her
people
very first
learning
order is a
this for
telephone
the first time
order.
in high
And so
school
we'll have
feel.
0.1. What's the probability that C equals 2? Well, it's the probability that her first order is not a telephone order. So it's 1 minus 10%. There's a 90% chance it's not a telephone
Pretty
order. And then her second
intuitive,
order is a telephone
I think.
order. What about the probability C equals
But
3?
it does
well,
help
her
that
first two orders
Sal is a
would
good
not be
teacher.
telephone orders, and her third order would be 1. And then C equals 4. Well, her first 3 orders would not be telephone orders, and her fourth one would.
Easy.
We could get a calculator, maybe an E thing. Probably this is going to be equal to 1 minus. Let me do this in another color so we know what I'm referring to. So what's the probability that we have no telephone orders in the first 4 orders? Well, the probability on a given order that you don't have a telephone order is 0.9. And then if that has to be true for the first 4, well, it's going to be 0.9 times 0.9 times 0.9 times 0.9, or 0.9 to the 4th power. So this is a lot easier to calculate. So let's do that. Let's get a calculator out. All right, so let me just take 0.9.
Ah, I see what he's doing. Fewer than 5 orders for Liliana to get her first telephone.
9 first order in the first 4. Is less than 5. That's the same thing as 1 minus the probability that we don't have a telephone order in the first 4. 1 minus the probability that no telephone order in first 4 orders.
And that's just the same as saying no telephone order in 4 orders.
We don't. I'm 0.2.
Okay, that makes sense. TI-84.
What we're going to do in this video is learn how to use a graphing calculator, in particular a TI-84. If you're using any other TI Texas Instruments calculator,
We
it would be
will
very
skip
similar.
ahead because I don't need to know this calculator stuff. Never gonna deal with one. Just need to know principles. Okay, find the probability that it takes at least 6 patients until the emergency room receives the first uninsured patient. 15%. First uninsured patient. So 6 or more, so 5. 5 patients are insured. 0.15. Power of 5. Nope. 0.85 to the power of 5. And then we do we do 1 minus this? Well, this is the same as saying what's the probability that the first 5 patients were all insured. So I guess that's the answer. It could be 1 minus, but no. No. VB, the number of vehicles registered in a day. What is the probability that she registers the leased vehicle within the first 3 vehicles of the day? Within the first 3. So it means that she's asking, okay, within the first 3 vehicles, they are, there's at least one. The only condition not to satisfy that is, we would do 1 minus 0.06 to the power of 3. That's 3 leased vehicles in the first 3. And the opposite would be 1. Show a step. What did I do? 0.06. Least not. That's what I did. Do all the hints. Least, not least, not least. Ah, wait. What? Wait, hold on. Okay, what's the probability? Probability of going least. Ah, not least, not least, not least. Ah, okay. Well, careless mistake. I was on the right path. Okay. Takes less than 3 frames to bowl her first strike. So, in 1 or 2 frames. Strike in the first, strike in the second. Strike in the first. And strike in the second. Fewer than 4 attempts to make his first shot. So, yeah, so 3 and at least 1. So if it's none, be 3.75. 3, 1 minus this, 1 minus that. 0.58. Bonus question. From experience that if he does not review a new vocabulary word that he has learned, he'll forget it 70%. Find the probability that it takes Anand 4 or more days to forget the word. 4 or more days to forget the word. This is the same as saying he remembers a day. He remembers the word for 3 days at least. 0.3. That's the chance he forgets it each day. 3. Wait. Find the probability that it takes Anand 4 or more days to forget the word. In other words, he remembered it for 3 days because he's very forgetful. So 3 days in a row without forgetting. And the next day he can forget or remember and then forget the following day. Okay. So I think 0.027 is a good answer. Yep. Okay. Let's do the last quiz and then we'll do the unit and then probably... Oh, we might be able to start in the following thing. 5 questions. Mean and standard deviation. Okay. B is the number of items that Jamie verifies to reach the first item that is checked out. 0.03. 1 divided by 0.03. 33. Standard deviation is 1.97. 0.97 divided by 0.03. 32.8. Find the probability that it takes Zach 2 or fewer throws to score his first ringer. Score a ringer. Score his first ringer. Two or fewer throws to score his first ringer. 2 or fewer. Okay, so 1 and 2. So binomial. Yeah, okay, instead of geometric. Or this might be geometric. So fail, fail, succeed. Then take a break. Okay, we're back for the last stretch for this video, so let's start. And okay, that's fine. I won't look at that. Mhm, mhm. Divided by 0.21, 0.2. Yeah, nice. Okay, now we do the unit test. Yeah, it shouldn't be too long. 24 minutes to do it. This should be neither, because it specifies you only have 1,000 employees. Geometric. Interesting. Are you joking me? Ah, that's so lame. Could I like... Oh, that's so stupid, but why? Andy and Jim are going to compete in the 100-meter dash against each other. Let A be the time it takes Andy to complete the race. J be the time it takes Jim to complete the race. Based on previous results, they know that 11.5 and then 1 second. They also know that... Okay. Find the standard deviation of D. Might need a refresher here. Christ. Oh, man. Okay, so the difference 11.5 minus 10.5. That's going to be their new mean. And then can't remember how to do standard deviation. It's really annoying. I don't think you just minus it. I'm gonna feel so stupid. See how we answered this question. Fuck's sakes. We'll just go through a bunch of questions and then we'll just redo the whole thing. Between their times is 1 squared plus 0.5 squared. This is literally the formula I was looking for and I could not find it. So stupid. Next question. Find the mean and standard deviation of f. I guess we can just start over right away. Four or more days to forget the word. So he remembers for 3 days. Find the mean and standard deviation. just a geometric distribution, geometric random variable. 8. Not, bull, not, bull. Okay. So that's 1, 1, 2. Yep. Are you shitting me? What? Oh my god. There's no. Fuck me. Fuck, that's annoying. Kinda hate quizzes, to be honest. Should we start over? Should we keep going? Ah, whatever. Which of the following would find PET equals 2? 1/3, 6 attempts. 2 out of 6 attempts. Fuck! 5 times 5 times 5? Nah. Oh my god. 5 to the power of 3. No. It doesn't make sense. Oh, fuck me. Keep fucking forgetting this goddamn. Okay, if we get another wrong, then turn back. Uh, that. First digit less than 4. He also plans to give every 5 students additional points. 19.5 plus 5 is 24.5. And then addition doesn't affect standard deviation, but multiplication does. So calculate standard deviation x. Fuck, I keep forgetting how to calculate standard deviation. God damn it. Fuck, it wasn't even asking for... No, it was. Wait, what? Okay. 0.2 is outside. Fuck me, no. Start over. God fucking damn it. Time is even. Need to go soon because meeting with the clients. Fuck. Pause. Okay. Start again. Okay, let's just solve these things one by one, and if I don't know, then I won't guess. I'll just look for the answer. Okay, 60% of a certain species, whatever. Mean standard deviation. Okay. Mean is that 1.7. That live. So square root of 0.4 divided by 0.6. 1.1. Oh my god, it wasn't geometric or something. I don't know. Fuck. Neither. Restart. Let's go. I'm so trash at doing quizzes and stuff, but it's also because I don't remember everything. Okay. Heather has a coin. Let X represent the number of heads she gets. Probability that she gets exactly 3 heads, so yep. 5 times. Oh my god. Okay, I think I'm going to take a break. Or you know what? No, we'll keep going. Let me extend this. This is geometric because it's saying until he misses one, so it keeps going. So how we calculate the mean here is 1 divided by 0.8, 1.25. And for the standard deviation, be square root of 1 minus 0.8, 0.2 divided by 0.8. Wait a minute, until he misses. Oh, wait, hold on. Actually, the other way. So 5. Square root of 0.8 divided by 0.2. What is the probability that he answers fewer than 2 questions correctly in the last 6 questions? Cumulative, binomial cumulative probability. Fewer than 2, so that's 0 or 1. Okay. Phi. Probability x equals 0. Okay, for this case. 0. Questions. Then x exactly 1 would be 0.25 times 0.75 times 5 times 1 choose 6. That's just 6. A division of a company has over 200 employees, fixed trials, 48% of which are male. Yep. Okay, so fixed probability. The company is going to randomly select 10 of these employees to attend the conference. Let Z equals the number of male employees chosen. Um, it's actually not fixed probability because there's no replacement. So every time you choose someone, there's one less male or one less employee, so that affects the stuff. Really now? That doesn't make sense. Wow. What the fuck? Oh my fucking god. D is greater than or less than 2. Equal to or greater than 2. Okay. 1 minus 0.3. Boom. Which graph correctly displays the probability distribution? Okay, don't fuck this up. So easy. 0.3. Has to be that one. Find the standard deviation of t. Okay. Let t be the total mass of the 4 dots. What is standard deviation? One of these fuckers again. Okay. It'll be... Okay, can't be that one. Or just 0.25. squared times 4 square root 0.5. This is one of the one of the questions I got wrong earlier. Okay, so let's try and write it out. Probability is 0.64 plus 0.32 uh oh, plus 0.04. Okay, now we do 0, 1, and 2. We do 0.4, 0.4, 0.4. Okay, so this will be 0.4 squared, 6 squared, and 1.6 squared. Let's go ahead and do each one before we add them. Squared plus, okay. Let me square root this. And that should be the standard deviation. Thank God. A certain basketball player regularly shoots sets of 2 free throws. The table below, okay, the number of shots, and then 2 people make statements. This is expected value. The expected value is 0.8. The probability that this player makes a free throw is 0.8 on average. Oh, is that right? Priya might be right, but no, I think they're both wrong. I really want to get it right. Neither statement is correct. Okay, let's see why the first one is wrong. Okay, that's what I was thinking. It's an average, not a probability. When Jordan wants to play a basketball game at a carnival, the game costs the player 5 to play. Okay, calculate the mean. And the player gets to take 2 long distance shots. If they miss both shots, they get nothing. If they make one shot, they get their $5. They get $10 back. Here's the probability distribution of X. M is the amount of money gained from playing the game. Okay. And I think we are just looking at money gained and probability. So what's the expected value of this game? So we just do -5 times. Wait. Binomial, random variable, mean. No, probability distribution, table, mean. Do we plus or do we times or do we divide? Plus, okay. 1, 2 over 6, 2. Wait, what? So that's the number. That's the probability. Oh no, we're just adding them. Okay, that makes sense. So these add up to 1 already. Okay, so we're just adding them. Just adding them. No, that makes sense. We're not calculating a probability. We're expecting... Yeah, okay. Average. Long-term average. Okay. Plus 5 times 0.16. -1. Oh, mean of X. Whoops. Not money. Okay. .8 shots being made. A division of a company has over 200 employees, 40% of which are male. The company randomly selects 8 to have lunch with the CEO. Okay, this is binomial, whatever. Binomial, normal, random variables. Okay. I think it's just like that. Each month. Each month. No, wait, no. 8 times 0.4, that's it. 3.2. And the standard deviation would be... I think it was like... So it's n times p, and then p times 1 minus p, and p 1 minus p. Okay, so we just get the square root of that, right? So NP 1 minus P. 8 times P, which is 0.4 times N minus P. 1 minus P is 0.6. And then we get the square root. That should be the variance. 1.4. Carnival ride has cars that each hold 4 adult passengers. The weights of the passengers for this ride are normally distributed with a mean of 65 kg and a standard deviation of 12 kg. Assume the weights of passengers are independent. Let T equals the total weight of 4 randomly selected adult passengers for this ride. Find the probability that the total weight is less than 242 kg. Okay, so this is a normal distribution problem. Z-score. No. Okay. 4 adult passengers. How would we do this? So we do something like that. 65. Because they're all the same, I think we would just I want to say multiply it by 4. If we multiply this by 4, it would just move that way. And standard deviation and mean would both be scaled proportionally. So 65, 130, 260, and then the standard deviation would be 48 kgs. And this is now the distribution of the sum of 4 passengers. 4x. Like that. Find the probability that the total weight is less than 242 kg. Okay, so below 242. And we have a mean of 260 and a standard deviation of 48. Below 242. 0.35. 538. Oh man, fuck no. Ah. I calculated the goddamn standard deviation wrong again. Fuck, I keep. Oh, in what world do you calculate standard deviation like this? I'm talking about myself, of course. I'm wrong. Uh. Greater than 10 barcodes before it misreads one. So it does not misread one for the first 10. So 0.95 times 10? Oh, not times, the power of 10. Oh, bada bing, bada boo. Find the probability that the 8th background check is the first for which the potential employee has not yet interviewed. Okay, so 91%. This can also read as 9% have not yet been interviewed. B is the number of blah blahs who have not yet been interviewed. Find the probability that the 8th background check Fion processes is the first for which the potential employee has not yet interviewed. Has not yet. So the first 7 are interviewed, the 8th is not interviewed. So simple as 0.91 to the power of 7, because the first 7s have been interviewed, multiplied by last one, which is 0.09, has not yet been interviewed. So company, randomly select 4, 60% of them have children. Which of these following would have probability? Okay. 4, choose 3. 60% of them have children, so that's first, and then, okay. Yeah, that one makes sense. 4, choose 3, 0.6 to the power of 3. Makes sense, because the first 3 have children. One guy does not have children, and then combinations. Okay. Leo selects 25 grandparents at random from his town to interview. In the town, 35% of the grandparents have their children living with them. Let G be the number of grandparents Leo interviews whose grandchildren, are living with them. This is a small number, so Leo selects 25 grandparents at random. I want to say neither. I'm not sure if the sample size is big enough. But let G be the number of grandparents. So there's, okay, independence. Might be independent, doesn't really say. Independence. Outcomes don't affect one another. Fixed number of trials. Success. Fail. I'm gonna say binomial. Don't overthink it. Hell yeah. No. Okay, let's go back and do these because I've been getting owned. Okay, and that is the last one for today, but let's quickly brush up on a couple of things because I don't like the look of yellow. Okay, find the probability. Okay, total weight of 4 apples. Mean 175 times 4. Okay, and the standard deviation 15 squared times 4. Square root is 30. $730 is greater than 736. So it's between we're getting the difference here, so okay, how do we do this? 20 minus 18, that's our new mean, and then 6.4 squared plus 4.8 squared Because we're still getting the difference. Square root, it's 8. 8. Between 10. Find the probability that the total weight is less than 242. Below 242. 260. 12. Power of 2 times 4. Square root. 24. Something like that. Woman is taller than the man. Okay, so let's get the difference. Done. And 9 is standard deviation. And this below 0 makes sense. So the difference is actually negative. Yeah, because men were taller than women. Okay, so below 0. Yep, let's just go with that. Which of the following choices can be considered binomial random variables? I would say this one should not be, because if there's no replacement and it's only 20 pence, then can't assume independence, I think. Container holds 1,000 pens, half of which are red. Select an SRS. X a binomial variable, why or why not? I'll say no, because 10% can't assume independence. Which of the following choices can be considered binomial random variables? That's one. That's one. That's one. Okay, so independence, outcomes don't affect one another, success or fail. Ooh, fixed number of trials. Z, a binomial variable, why or why not? No, because there's not enough, there are no fixed number of trials. Easy, okay, so, cool. Time check, 2:30, okay. I'm a bit over time and I should not have done that, but I just wanted to finish up this unit. So let's quickly wrap up. Quickly wrap up Unit 9, Unit 8. We dealt with different types of probability distributions, different types of random variables, geometric, binomial. We talked about cumulative probability. We talked about, trying to remember what it's called. Let me actually go back. Unit 8. Well, there's quite a bit of stuff to discuss. I'd say the main thing that we did today was geometric and binomial random variables and how to deal with the different distributions. Also, mean and standard deviation. Mean, also known as expected value. It's different for if you're calculating it for a binomial or a geometric distribution, or sorry, geometric random variable. The main difference between binomial and geometric variables, random variables, is that binomial distribution will have a fixed number of trials, so the question you're trying to solve usually is what's the probability of getting a certain amount of successes? So something like, what is the probability of rolling 3, having rolling 3 threes, rolling a 6-sided dice 6 times, for example. That's a bad example. It was kind of wordy, but if you replay my video, you'll get what I'm saying. And then a geometric random variable is something like how many turns will it take before Rocky rolls a 6. And so you don't have a fixed number of trials. You're trying to figure out how many trials it'll take to achieve something. And then there are slight variations to those questions, but they are kind of rooted in, yeah, that type of variable. What other things? Proof. Oh, I didn't see this a while ago. But that was it. So we did the unit test. We talked about random variables and probability distributions. I was still making lots of mistakes by the end of it, but that's fine, because I think I've got the gist for sure. And a lot of the mistakes I was making were, careless mistakes, not knowing the formulas and stuff. That doesn't take away that I understand the stuff I've studied. But yep, Unit 8 done and dusted. Can't wait to move on to Unit 9. So if you enjoyed the video, leave a like, leave a comment, leave a subscribe, and I will see you on Friday, tomorrow. Okay, peace.